Turn to the left and now look down. In this movie, we take a closer look at the interaction of carbon dioxide molecules with calcium oxide, also called quicklime, which is an important natural process that is also used in industry. The movie is the result of an electronic structure calculation. Calcium atoms in the surface are represented by gray spheres, the oxygen atoms by red spheres. The carbon dioxide or CO2 molecule is shown as a white sphere, the carbon atom, between two red spheres, the oxygen atoms. When CO2 is far from the surface, the molecule is linear. What governs the interaction that we see when the molecule approaches the surface? The atoms are held together by chemical bonds created by the electrons. When the CO2 molecule gets close to the surface, the electrons redistribute. We now take a look at the charge density of the electrons, shown in yellow. What exactly happens to the electrons is hard to spot here, as the changes are small compared to the overall value of the electron density. Therefore, it is a good idea to compare the situations when the CO2 molecules are far away to when they are close to the surface. In other words, we take a look at the difference of the electron density in the two scenarios. Now, the red color reflects an increased electronic charge density, while the blue color marks a depletion of electrons. The new shape of the electronic charge density indicates that the formerly very stable CO2 molecule is now ready to undergo the desired chemical reaction. The process is shown in slow motion. In reality, it happens 20 billion times faster. Why is this interesting? Carbon dioxide is a highly problematic greenhouse gas that is produced, for example, by cars, as well as in the steel and cement industries. CO2 emissions are the main reason behind man-made climate change. However, in principle, it is also possible to use CO2 as a beneficial raw material for making valuable chemicals, including fuels for transport and for heating. Movies like this allow us to observe processes that are a quadrillion times faster than a blink of the eye and to see atoms and molecules that are tens of millions times smaller than a grain of sand. This helps us to look deeper than ever before into the processes at the surfaces of catalysts that are used extensively in industry to accelerate chemical reactions. The NOMAD teams in Barcelona and Berlin are working towards a deeper understanding of catalysis, which will enable, amongst other things, new, more efficient catalysts for CO2 conversion to be developed.